Cities across the world are facing a growing and often invisible challenge: chronic urban heat. Unlike short-term heat waves, chronic heat builds slowly over the years and decades. It is driven by rapid urbanization, increasing built-up surfaces, loss of vegetation, and changing climate patterns. In dense urban environments like Jeddah, Saudi Arabia, this effect becomes even more pronounced. High-rise buildings, asphalt roads, and concrete surfaces absorb and retain heat during the day and release it slowly at night, creating what we call the urban heat island effect. But here's the real problem: heat is not just an environmental issue, it is a risk, and then risk depends on three key factors. The first one is the exposure. It tells us how hot a place is and how that heat is changing over time. The next one is the sensitivity, which tells us how many people are exposed to that heat. And the third and last is the adaptive capacity. This tells how well the environment can absorb or reduce that heat. With these three factors combining, we define the Chronic Heat Risk Index or HRI. This will be our case study and demonstration in this video. So let's create a new chat and rename it based on our objective. As we begin, let's upload all the required datasets into this current session. First, we are uploading the Landsat derived land surface temperature rasters spanning from 1984 to 2025. These are sourced from USGS Landsat missions, which include the datasets such as Landsat 5, 7, 8, and 9, providing a 30-meter resolution for the thermal data. Let's wait while the rasters upload into this session. Great. The Landsat datasets have been uploaded. Next, we use the ESA WorldCover land use land cover data. Let's upload it. It is a global 10-meter resolution dataset which helps us understand where vegetation, built-up areas, and barren lands are present. Great. The LULC raster is uploaded as well. Finally, we also upload the population data. The population data is typically sourced from the WorldPop website, which provides gridded population estimates at a 100-meter resolution. Great. All the datasets have now been uploaded to the session. We can check them into the data catalog. Importantly, all these datasets, right from the Landsat, the LULC, and the population data, are open source datasets and have been widely used in different types of GIS and remote sensing applications. We can begin by visualizing some of these datasets on the map. Let's check out some of the LST rasters. We can also check the LULC raster on top of it, or the population raster as well. Before beginning any analysis, it is important to understand the quality and structure of our temperature data, as this is the base of this and foundation of this analysis. In this step, we will examine all the land surface temperature rasters first. Here, we have asked the system to automatically identify all yearly data sets, checking their consistency and ensure that they are aligned spatially, have same resolution, extent, and same coordinate system. Later, we will also verify the temperature values and check whether they are in degrees Celsius or Kelvin, which is critical for accurate interpretation. At this stage, we are essentially ensuring that the foundation of our analysis is reliable. Once this is confirmed, we will proceed for the actual analysis. Great, the agent has come up with the results and we can see what we have in store for us. As we can see, CRS is consistent across all the years as well as the resolution and the spatial extent as well as alignment. There are no missing years and continuation is present from right from 1984 till 2025. And as per the agent, we are ready for processing into the next steps. Let's begin the analysis. Instead of stacking multiple rasters, which can be computationally expensive, we adopt a more efficient approach. We convert the rasters into a point grid where each pixel becomes a point. So let's start the process. Here, finally, each point will represent a 30-meter location on the ground carrying the temperature information. This approach allows us to efficiently store the data, perform fast calculations, maintain high spatial precision. Eventually, this output will become our master analytical dataset, which will drive the entire workflow. Great, the HRI master points grid is created. We can visualize it on the map. We can even check the attribute table where the XY, that is the latitude longitude coordinates for each point are also populated. Now we extract the temperature values for all years into this point grid. Based upon the results, each point will hold a time series of temperature values right from 1984 to 2025. This is a critical transformation. We are converting spatial data into temporal intelligence per location. This allows us to track how each location has behaved over the decades. Let's wait for the results the agent will generate. Great, the results have been generated. Let's check out the attribute table of our master grid to see whether the columns are there. As you can see, the LST columns for our whole time frame have been extracted. Next, we calculate two very important metrics. First one is the mean LST, that is the long-term average temperature for the time period, and the LST trend, which tells us how temperature has changed over time. The trend will be calculated usually using a regression and expressed in degrees Celsius per decade. This tells us not just where it is hot, but where it is getting hotter. This is the core of chronic heat exposure. Let's wait for the agent to generate the results. Great, the results have been generated. As per the agent, the statistics are minimum mean LST temperature is 31 and maximum is 49.68 with mean ranging near 45.5. Similarly for the trend, minimum value is minus 0.76 whereas the maximum value goes over 4 with mean ranging near the value of 2. We can check out the attribute table to see where the points where the calculations are completed. As you can see, two new columns, mean LST and LST trend, have been generated correctly. Now, to understand the climate change impact, we compute the temperature anomalies. We compare a historical baseline period, that is from 1985 to 89, and a recent time period, that is 2021 to 2025. This difference gives us how much temperatures have increased over time. Areas with high anomaly usually indicate rapid warming zones. Again, let's for the let's wait for the agent to generate the results. Great, the results have been completed. As you can see, there are many areas where the trend or the anomaly of rise in temperature is found. We can see that there is close to 2 degree rise average temperature throughout the region of interest. Let's check out the newly created column in the attribute table. As you can see, then this new column for LST anomaly has been created. Now we bring in the land use land cover data. We classify each location into three categories, mainly vegetation, built up areas, and barren land. Eventually, from these three classes, we compute the adaptive capacity, representing these three classes. Vegetation usually helps in cooling, therefore represents high capacity, whereas built up areas trap the heat, so they represent low capacity. This step introduces environmental context into our analysis for calculation of heat risk. Great. The land use land cover classes as well as the adaptive capacity have been computed. Let's check out the attribute table to visualize it. As you can see, this new column AC represents the adaptive capacity, which ranges from the value of 0 to 1. As briefly discussed during the introduction part, heat risk is not just about temperature, it's also about people. So therefore, let's bring in the population data into this context. Here, we redistribute the population data from the 100-meter resolution dataset from the WorldPop to our 30-meter grid. But population is not evenly distributed. Therefore, here we are assigning population only to the habitable areas. This avoids unrealistic allocation in deserts or water bodies. This step ensures accurate human exposure modeling. Let's wait while the agent computes these results. Great, the process is completed. Let's check out the new columns into the attribute table. As you can see, this POP underscore 30 meter represents the population redistributed to the habitable areas. Next, we convert this redistributed population into density. This gives us people per square kilometer, allowing us to identify high density residential zones, low density or uninhabited areas. These are our sensitivity hotspots as well. Great, the results have been generated. Let's check out the attribute table once again briefly to see the newly generated feed. As you can see, the population density is present in the new attribute table. Since now all the variables required for calculating the heat risk index are extracted to the grid, we normalize them in the range of 0 to 1. This ensures fair comparison across variables and balanced contribution to the final risk. Based on this normalization, we will now have exposure index, sensitivity index, and the adaptive capacity index. Great, the results have been generated. Let's once again check the attribute table. As we can see, these three new indices, E that is exposure, which represents the land surface temperature over the period of time, sensitivity, which represents the population dynamics, and S log that is we scale the sensitivity to the logarithmic scale, again in the range of 0 to 1. Now let's combine all these three parameters into a single index representing the heat risk. The heat risk index formula is defined as exposure plus sensitivity, which is added to the subtract difference of 1 minus adaptive capacity, which throughout is divided by 3 to get the mean. This will showcase areas with high temperature, high population and low vegetation will be highlighted. This will be our final heat risk index. Great. The HRI calculations have been completed. Let's check out the new column created into the attribute table, which represents our final heat risk index. Nice. As per the agent, which has also calculated the statistics, the HRI ranges from minimum value of 0.14 to the maximum value of 0.91, with the mean ranging near 0.7. All these values are in the range of 0 to 1. Since all the computation on the grid is completed, let's make the results visually more intuitive. For that, the results are now converted back into a raster format. This will allow us to visualize spatial patterns, generate maps, and share outputs easily. We will now have spatial heat risk surfaces. Great, the analysis is completed. Let's check out the newly generated rasters on the map. First, let's start with the HRI, which has the minimum value of 0.14 and the maximum value of 0.91. As you can see, most of the area is in white color representing high ranges. Only few regions where low value is present. Let's check out and switch on the satellite imagery to see what exactly is present in this region. As you can see, some part of vegetation has resulted in the decrease in HRI as it ideally should. Similarly, we have also generated the mean LST, the LST trend and the LST anomaly, which showcase the increase in temperature over the period of time. Now, to draw meaningful insights, we classify each region into a different types of hotspot categories. This will help us identify extreme heat risk zones, emerging heat zones, as well as cooling areas. This step transforms raw data into actionable zones. Great, the results have been generated. As you can see, the agent has also provided us the area distribution for different classes. The extreme hotspot range, where severe temperature rise is there, is close to 88% in the study area. And secondly, is the emerging hot zones with the value of 11 to 12%. We can also see the generated CSV table to see the area matrix. This calculation to see how much area falls into each hotspot category gives us a macro level understanding of this heat distribution and risk spread across the region. As you can see, majority of the area is in the extreme condition, which signifies the high risk in the given region. Let's ask the agent to generate some insights automatically. As you can see, the agent has generated a summary and insights based upon the results that were present. Before jumping into direct manual analysis, we can see the analysis or draw insights in automated way by the agent. As you can see, the agent is also providing us with different types of measures that need to be carried out for different zones. As in the structure table, for the extreme hotspot region, which is predominant in our area, the agent is providing the measures such as dominant heat core, priority zone for immediate heat mitigation and protection. Now, now let's connect these insights to the real world. We will identify high risk zones, important locations in the study area, such as different residential clusters, commercial hubs, roads, and infrastructure. This bridges analysis with real world impact. Great. The high risk zones have been identified and the clusters have been generated. We have generated a summary table for the top 8 high risk zone scores based upon their priorities and even generated the map out of them. Let's visualize it on the map. As you can see, these clusters have potentially very high heat risk and have been clustered into different urban pockets, which is potentially correct. Now that the high risk zones and raster surfaces have been generated, we can link them to the real world locations more accurately. Now, instead of relying only on the nearest point, we first check POIs which falls directly into these identified high risk zone clusters and then extract the local heat risk. This gives us a much more realistic understanding of which important urban locations are actually exposed to the highest level of risk. So let's proceed. Great. The agent has completed the results. The agent has successfully generated the POIs for different types of categories like commercial, industrial, public infrastructures, even education such as schools and universities and transportation hub, and generated at filtered top 10 POIs. We can visualize them on the map. We can also check out the attribute table to see their category. Similarly, we can see even more points of interest of different categories if we specify that to the agent. Great. Now, finally, we will generate some decision ready conclusions. Now, we need to understand it from the agent that what is driving the heat risk here, what interventions are needed, and which areas are most vulnerable. So let's transform this data into urban planning intelligence. So let's begin up with our final prompt. Great, the agent has come up with the final conclusions. As per the agent, the HRI and the hotspot outputs isolate a coherent urban risk score where extreme hotspots are present in close to 46 clusters in the study area. These risk clusters are concentrated into small number of dominant clusters out of these 46. Apart from that, the agent has also come up with the measures or preventive steps that need to be taken for cooling and adapted measures required, such as increasing tree canopy and shade structures in certain areas, deploying cool pavements and cool roofs, targeted heat safety measures for institutions like schools and other education centers, site scale retrofits for large paved parcels. Similarly, even without human intervention, the agent is able to provide such detailed insights and conclusions based upon this workflow. Now, to end this demonstration, I would like to mention that this workflow we were able to process from raw satellite data right through the actionable insights, which has been executed seamlessly within GriidAI. Without writing complex code, without manual processing, without switching tools, GriidAI enables faster geospatial analysis, intelligent automation, scalable workflows, and decision-ready outputs. In just a few prompts, we have built a complete urban heat risk index model. This kind of analysis can support climate resilience planning, urban design decisions, and heat mitigation strategies. GriidAI is not just simplifying GIS, it is redefining how geospatial intelligence is generated. And this is just one of many possibilities.